right, gang, welcome back. Happy Monday. Today is our 28th class of the semester. We're covering something called linear and quadratic approximation, and we're going to relate those two things to the derivative. Just in terms of what's coming, again, data and rainbow, hopefully we're making steady progress along the way. I know some of us have made excellent progress and are essentially done with one or both of these, which is fantastic. So if you have time, get going on those two. You don't need to follow the timeline there. We will have a take-home quiz that I'll give you on November 21st, so that's coming up in a week. And also there is a related rates in-class quiz. I'll tell you about that when we get there. But I think I mentioned you're going to be working together with each other on that quiz, which is different from all the other quizzes. Questions on the calendar? Okay. So we're starting on the top of page 16. In this class, we look at two powerful approximation techniques used in applied mathematics when a function is just too complicated and messy to work with. So the basic idea for today is that we've got some function that's really crazy complicated, and we just don't want to mess around with it. And so we're going to try to approximate that function with something that is a lot more user-friendly for us to actually do calculations on. So before we jump in and do a specific example, I wanted to show this graphic. So what function is this here? Sine, right? Let's see. So top is 1, the bottom is -1. It goes right through the origin there. The first positive x-intercept? Pi, right? It looks like around pi. Okay, sure. And then, and then 2 pi out here for the next one, and then it's got this symmetry through the origin. Okay, so that's great. So so I'm going to take the screen and drag it to the left, and we're going to see more stuff with pi. So what number is out here? How many pi's is this? That's 4 pi right there, right? Okay, so no problem. So we just keep dragging to the left, and then what happens? It goes up. Is this the sine function? For sure, this is not the sine function, but it sure tricked us for a long time. Turns out this is a polynomial of degree 49. X to the 49 plus x to the 48 plus x to the 47, some coefficients in front of those guys. So that's kind of a surprise. And what's really a surprise is how closely this thing resembles the sine function. So I'll put up in blue the sine function. Now I'll hide it again. You can't see any difference here, right? They look exactly the same. So as I drag the x-axis inwards, we'll eventually be able to see the sine function continuing in blue, just like the sine function does, but then the polynomial eventually leaving it someplace out here in the mid-teens, okay? So that's pretty weird, right? To see a polynomial that mimics a sine function so closely that we can't even tell them apart for, I don't know, a good 15 units in either direction from the origin. I will show you some parts of the formula. I don't think the whole thing will fit on the screen, but anyway, there's the polynomial. It's x minus x cubed over, what's this exclamation point? Factorial. And what does 3 factorial mean? 3 times 2 times 1. That's what 3 factorial means. So this is really x to the 3rd over 6 plus x to the 5th over 5 times 4 times 3 times 2 times 1. That's 120. What's that? This is this choice the software designers made. So like I said, I can't show you the whole thing because it's a 49th degree and I just don't have enough pixels on my screen to show you. But in any event, that's where we're headed, is to take a function and approximate it with a polynomial. That's the ultimate goal, okay? Now, we're not going to get to things as complicated as this guy today. In fact, we're not going to get to things as complicated as this until Calc 2 next semester, but we will do this next semester. But anyway, that's sort of the preview of coming attractions. So we're going to start with something simpler here in number 3. So we're beginning with the formula f of x equals square root of 1 plus x, which admittedly is not that awful of a function to start with, but we got to start someplace. Suppose that suppose that I asked you for the square root of, say, 1.1. What would you do? What would you do? You'd use your calculator. This is not a hard problem, right? Okay, but 50 years ago, what would you do? Yeah, you could do a guess and check. What do you mean, Troy? Mm-hmm. And so, yeah, so maybe we try something like 1.03. And what should we do with 1.03 if that's the right answer? We should square it, multiply it by 1.03, and we're hoping it's 1.1. And if we're too big, we make 1.03 smaller. And if it's too small, we make it bigger, right? And you can guess and check. And you can imagine that, you know, like if eventually you get like that much accuracy, like how awful would it be without a calculator to square this number, right? Just think, it's not hard, it's very long. So I'll say that what we're about to do here has a little bit more significance historically than it does today, given how easy it is for us to just find the square root of 1.1 on our calculator. But even, but that piece aside, it's still pretty darn cool that we could fool ourselves into thinking that a polynomial was actually the sine function, right? So that's where we're headed next semester. But let's try this one for today. Here's what we're going to do. We're going to approximate that guy right there with a linear function that behaves similarly to the original function near x equals 0. And here's our technique. We are going to find f of 0. 0 is part of the problem. How much is f of 0? Okay, so f of 0 is 1. That's fine. And we're also going to find f prime of 0. F of 0 and f prime of 0. So let's find f prime of 0. But we can't do that until we have f prime of x. So we're going to build L in a second, but right now we're just playing with F. Yeah. Okay, so how do I take a derivative of this? Well, we just have to write it as 1 plus x to the half, yeah? And then we do our chain rule. So half comes down, copy the 1 plus x to the negative 1/2 times what? Times 1, which is the derivative of what's in the parentheses. Okay, so there's our derivative. Let's write this in a slightly more user-friendly way. So I think this is really just 1 over 2 square root of 1 plus x. So there's our derivative. And again, we're going to plug in 0. 0 was given in the problem. So let's find f prime of 0. So just plug 0 into the derivative. I get 1/2. So far, so good. Okay, and so what we're going to do is create this, this linear function, this L of x thing, and we're going to make sure that our linear function agrees with this original function, both at the point, which is 0, 1, and it's going to have the right slope, which is 1/2. And so let's start with our L of x is going to be this generic linear function. I know typically we do mx plus b. We're going to do ax plus b for reasons that will become clear in the activity. Let's go ahead and find L prime of x, the derivative of that guy right there. What is it? Yeah, that'll be our final answer, yes. So the derivative of this thing right here is just a, right? Yeah, you're ahead of us here. We're gonna get there. Okay, and so let's find L of, I'll do one more color here. Let's do L of 0 and L prime of 0. And I think once we finish these calculations, everything will sort of come together here. So how much is L of 0? It's just b, right? Because we're plugging 0 in for that x. So a times nothing plus b, which is just b. And how much is L prime of 0? It's a, it's always a. Normally there'd be x's to plug into, but it's just a. Okay, and so now we're going to put everything together here. What I really want is for L of 0 to match exactly with f of 0. I'm just trying to make these two things the same at that one spot, which means how much is b? It's 1. And likewise, I would really love for f prime of 0 to equal L prime of 0. I'm going to make my new function have exactly the right derivative, at least at x equals 0. After that, who knows? Which means how much is a? 1/2. And so we just have to rewrite this guy to get our final answer. L of x equals, we said a was 1/2. I'm copying my x plus, and then we said b was 1. So there's our linear approximation, 1/2 x plus 1. Okay. And if we were to graph, we're just going to jump real quick to the activity right here in the middle of page 17. I did make a small change to the language, so if you came in after I announced that, go ahead and make that change. But the graph we're looking at here, the curve is the square root of 1 plus x. That's our original function. And then this thing right here is L of x, which we decided was, what was it? 1/2 x plus 1? Yeah, okay. So what did we find? We found the equation of the tangent line, right? That's what we did. I didn't ask you to find the equation of a tangent line. What we really did was make it so that our line touched at the right point, which was right there, and had the correct slope, the same derivative at that point. And so, yeah, we made the tangent line. But we didn't think about making the tangent line in the way that we've been doing all semester. Okay, so go back real quick. Number 4 here is our summary. Here's how we built the linear function above. We started by making our big bad function, that was the square root function, and our linear function have the same value at a single x value. It was x equals 0, but in general, x equals a. And then we made the derivative of our big bad function, that's the square root, and the derivative of our linear function have the same value at that same single x value, x equals a. So they agree at the point, same y value, and the same derivative. And we called that line that we just found here the linear approximation or the local linearization of that square root function at x equals 0 or x equals a in general. Okay. All right. So I think that's it in terms of the demo. The activity is here. Before you jump in on the activity, just a quick announcement. I'm going to make this announcement as I awkwardly stare at the brick wall back there. So nobody thinks I'm talking exactly to them. The very last day to withdraw from any class this semester is tomorrow, Tuesday. And so if you are thinking about withdrawing from this class or any other class, you need to get some paperwork done and a signature from your advisor before the end of business tomorrow. If you are considering withdrawing from this class, talk to me and I will give you my opinion on whether or not I think that's a wise idea. Any questions on that?
Not on that, but
yes.
The linear approximation at x equals a, so you could be setting it up to be any value of x.
Yes. Yeah. And so if we wanted the local linearization of this guy at x equals 2.5, then we would have a different line. Yes, f of 2.5 and also f prime of 2.5. Good? All right, any other questions?
2.5 becomes the b and the f prime.
So things became a little bit easier for us just because we happened to do 0. If we were to do 2.5, so we just made up a number here, but when we plugged 0 in when we did L of 0, what did we get? We got b, right? When we plugged in, right, we just got plain b, which was quite nice. But if we plugged in x equals 2.5, you don't get just plain b, you get 2.5a plus b, right? So what you would have then, I'll erase this in a second, is that 2.5a plus b is supposed to equal, so that's the L of 0, and we want it to equal f of 0. What was that? It was 1. Okay, so it's not as easy to solve that equation, but if we had another equation, like the two of them in concert, we could solve. If we plug in, let's see, in this case, 2.5 for x for the derivative, What do we get? L prime of 2.5. No. L prime of 2.5. It's just A. L prime is always A in this example. Okay, so that part would be easy enough. And we would have this A, and I'm trying to make the derivative match the derivative. So I'm trying to make that still equal to half. So that equation is still easy.
Would it still be a half though if we were doing 2.5?
No, that number would change.
Okay.
But it would just be a number.
Right.
Yeah. So then in this case, we'd have a system of two equations and we would solve them together. Right? You'll be doing that in the activity. Great. Any other questions? Okay, then go ahead and start on the next page and I will walk around and help.